A water jet will break up into drops, but why does this happen, and how can we use high-speed cameras in order to understand this phenomenon further? In addition, how can we adjust various parameters in order to control this behavior and measure it? Hello everyone, I'm just making this video to describe how my code works and what it is capable of doing. To start, I'll just briefly go over the libraries I'm using. I'm using the OpenCV library, which is imported as CV2, matplotlib, numpy, and I'm also using a separate Python script which imports my files, which are in the mraw file format from the Photron camera, into Python in a format that I am able to use it. To start, I will be just focusing on a particular function called single image thresh data, which is similar to this function, but it allows us to view some plots like you can see on the right hand side of the screen. The first few lines of the code just import the file into a image matrix, and it also works out how wide the image is, which is this length here, so going from 0 and then just over 300, and this is used to work out where the edges are. And then finally I just select the first image because I'm only looking at one image, but the code itself will later go through all the images, and I'll show you how that works. The main thing I'm using from CV2 is the threshold function, and this is a binary threshold, and I will show you how this works by using the plots on the right hand side of the screen here. This is a plain plot of an image out of the camera with no modifications whatsoever. When we apply a threshold, we turn these values of the pixels, which are 12-bit, so from 0 to 2 to the power of 12, or 4096, into binary numbers, either 0 or 1. So we've turned this grayscale image into a binary image, and you can see the effect that this has. If I show you the thresholded image, which is this function here, you can see that now the image is either black or it is white. There's no grayscale anymore. And this is very useful because then it allows me to detect the background, which I know is going to be 1, and the interior of the jet, which is 0. Now notice there is this white column in the middle here, and that's purely because water is transparent. So some of the light is actually passes through it, but we can ignore that because of the way the code works, where it will progressively go from the edge of the picture until it finds a 0, and similarly on this side it will do the same thing, and that's what these for loops here are doing. So here we have one for the left edge where it's going from a certain location and it's saying, is this 0, is this 0, yep, I found a 0, and similarly the right edge is going this way around, so it's just inverted, and it's going, is it 0, no, yep, I found a 0, so that's the edge. And we can also choose where we want it by prescribing its Z location. So in this case, my axes are defined as X in this direction, Z in this direction, and then Y is going into the screen. If we want to see what the actual output of this code is, we can look here, and we have found two edges, and I've simply prescribed, I've run this code, and I've said I want a Z location at 250, so Z equals 250 here, and it's run the code here and it said there's an edge here, and there's an edge here. Now we don't just want to do processing on a single image, in fact we want to do it on hundreds of images maybe, but in this case hundreds of thousands of images, because this is a high-speed camera that we have loaded data from. So the second piece of code that I'm going to show addresses that and runs the code over all the images. It's very similar to what we saw before, where we load the file and we just do some analysis to try and figure out how long it is and so on. I do some initialization of numpy arrays, but here's the key difference here. I've got another for loop where I'm running along all the images in the video. FFT stands for fast Fourier transform. I'll be showing an example using a sine wave, but to briefly go over what my code does, it is trying to find out the growth rate of these various frequencies by using curve fitting and also using those different Z locations that I showed earlier to trying to find out how the growth rate changes as we change certain experimental parameters. I won't be going through detail of this code, but I will show an example of an FFT and how it works. So let's say we have a sine wave, which is our signal to be processed. And you can see there's two sorts of frequencies going on here. You can see there's a major frequency here, and then you have this kind of more higher frequency noise signal occurring here. This is a 400 Hertz sine wave and a 4000 Hertz noise sine applied to it. So how would we figure out what this is if we didn't know that? Well, we can run an FFT on this, and then that will return a plot like this. And you can clearly see here that there's just simply two spikes. One is at 400 Hertz and one is at 4000 Hertz. So from taking this quite confusing signal, we've got a relatively straightforward graph. And this is what my code is doing, is it's trying to convert far more noisy and complex signal than this, and trying to see what the underlying frequencies are and their various amplitudes. So we can see the 400 Hertz is the dominant one, and there is a 4000 Hertz less prevalent one here. If there are any questions about my code, please do put them in the comments or send me a message and I will get back to you. Thank you.